Okay, we're going to be talking today about electric potential. I need to alert you to a couple of schedule issues. Last week, of course, we did not have school on Thursday and Friday. And because of that, there were a couple of things that were on this assignment sheet that never ended up happening. Would you mind hitting the door, please? Thanks. The first is that the assignment on Thursday concerning Gauss's law, we aren't going to do. If you'd like to do that for like brownie points, you can do that, but I'm not going to actually give a lesson.
Mr. King,
Charlie Tibbetts did. Yeah.
our band is going through something next week, and we have to have an emergency practice today.
I understand.
Okay. I have homework, but we just
Great. I'm going to report today.
Okay, thank you. I'll sit down here.
And the second thing is that the quiz that was scheduled for last Friday, we're going to do this Wednesday. So that will give you a chance to kind of catch up. But I'll put this on the assignment.
So that means no homework as a, so catch up on missing homework now? Or?
The Thursdays,
I know Thursday homework you don't do, but what about,
yeah.
like if you're missing stuff, or are you just catching up to that? Like,
Now, if you're missing stuff, you should have caught up over the weekend. Did you?
I didn't have time.
2 extra snow days and you didn't have time to catch up? Well, no. Okay. So, we're going to move on then to electric potential. And there's a compelling reason to do so. Our story so far has been a story of electric fields, and fields cause forces. Force equals charge times field. And if we have a single charge, sitting here, let's call this guy plus Q, then our single charge is going to create field coming out of it. How do I know it's out and not in?
Because it always went from positive to negative.
Yes, that's right. Field comes out of positive charges, goes into negative charges here. And the magnitude of the field at any distance r, so if I call this point A right here, which is the distance r from the Q, from the charge, then the magnitude at point of the field is equal to K times Q over r squared. And the distance we had to figure out by hand. And that became a pain in the neck because then I had to worry about some angle. You guys remember this from homework, right? I had to figure out some angle, and then I'd express it in terms of components and blah, blah, blah. And it is precisely that vector thing that makes it tedious, because if I have a charge configuration, where I have multiple charges, then the total field was the vector sum of all of the individual contributions from each of the charges, and we had to add those as vectors, which meant that we had to find the components, and then we had to add them all together, and it was a pain in the neck. You guys remember doing some problems like this last Tuesday and Wednesday. So this procedure, while it was not hard, was a tedious procedure, and we'd like to avoid it if we possibly can. And it turns out we can. But to avoid it, we need to concern ourselves with something different from force. Rather than looking at the forces exerted on charges, we're going to consider instead the potential energy of charges. So instead of force, let's compute energy. And this is a familiar procedure. You remember that we used work energy in a lot of different circumstances and potential energy when we dealt with gravity, right? We're going to do the same kind of thing here with our electric charges. In the missing lecture that we did not do on Gauss's law, I talk about a configuration, a charge configuration, where you have a metal plate with excess positive charge. And it's actually not hard to create a charge configuration like that. You just take a metal plate, a sheet of aluminum or something like that, and you walk across the floor, scuff up your heels, and you touch that plate. And when you touch that plate, then some of the charge will be transferred from you to that aluminum plate. And now, ta-da, you've got a plate with excess positive charge. Well, maybe if the charge is locked, but usually you can't generate too much static. Now, what happens to that charge on the inside? Well, remember that metal has the property that charges do what? Inside a piece of metal. They move around easily. Right. I don't know about transfer, but they move around easily. The reason I say I don't know about transfer is to get outside of the metal to transfer to something else, they require a little bit of energy. But within, they require no energy to move around. And so because the positive charges repel each other, what they're going to do is they're going to distribute themselves evenly throughout the metal plate. If the metal plate is not uniform, if it has some spiky points, then you'll get extra charge congregating at the points at the tips. So the charge is going to distribute evenly, and as a result, the electric field created by that charge configuration is going to be constant. And it's going to be straight out from the sides of the plate, just like that. At the edges right here, you'll get a little bit of fringing. So technically it starts to look like this. But we usually ignore the fringing out of the sides because what we're focused on is the constant electric field there in the center. Now the reason I mention all this is that this now becomes a kind of reference condition for us. If I want a constant electric field, I'm going to use a metal plate to make it happen. Does that make sense to everybody?
So basically what you're saying, like, for like electromagnets and stuff?
Yes, or capacitors. Capacitors are basically two metal plates that you charge up. You put plus on one and minus on the other, and now you have a nice constant electric field between the two. Yes?
Why do the charges come first?
They're basically kind of pushed out in that direction. Yep. I'm not even sure it's the charges themselves. It may just be that the electric field is stronger at this point. I need to check that. I'm not doing wrong on that. Okay, so we have a constant electric field. Now here's what I want to imagine, you to imagine. I promised we would talk about energy. So let's actually compute energy now. I want you to imagine that I have 2 points, A and B right here, and I'm going to put a positive charge plus Q at point A, and I'm going to force it to move towards point B. Now why do I have to force it? The positive charges, they repel. So I'm sitting here and I'm pushing this. And so what I want to compute is the amount of work done in moving a charge from A to B. Okay. So we compute that work as force times distance, right? And because we have a constant electric field, our force is a constant force. And so I don't have to worry about areas or anything funky like that. And in fact, I know the value of my force. The value of my force is equal to charge times field. So that the total work done in moving a charge against a constant electric field is going to be Q D times D, force times distance, charge times field times distance. Does that make sense to everybody so far? Good? Okay. Now, what I would like to do is to compare this to the gravitational case. Compare this to the gravitational case. If I have a waterfall that is of height h, and I have a bucket full of water that is of mass m, and I take that bucket full of water and I now move it to the top of the waterfall, how much work do I end up doing? H times the force. And what is the force? M times g, that's right. So that the total work done is equal to mgh, doing work against gravity. And when I did work against gravity, what happened to the work that I put into it? It's stored as potential energy. That's exactly right. And if I let go of the water, down it comes. That's exactly it. Do you notice the mathematical similarity between our two expressions right here? The distance here times the force. And the force in the case of the electric is charge times field. In the case of the gravitational is mass times gravitational field, acceleration due to gravity.
Is it because they're both fields that they're both so similar?
Exactly right. What we have is the constant field case here. And in the case of the constant field, charge times field times distance gives me work. In the case of the constant field, constant g, and we have mass times field times distance gives me work. And this energy is now stored up as potential energy, so that if I let go of my charge right here, located at plus q, what's it going to do? It's exactly right. And you guys have all seen that. If I take and give myself a lot of charge by scuffing up and do a little bit of this, what happens to my hair? Out it goes. Why? Because the positive charges are repelling each other, and they repel each other until they hit a point of minimum potential energy. They get as far away from each other as they possibly can, so it's minimized the potential energy.
And then each of your inputs pairs a positive charge.
That's positive charge. And the reason I know that is because they're standing out away from the others. And the only other force that's acting on them besides gravity is the electrical force.
I think it's from a negative charge.
It could have negative charge. Probably depends on what type of shoe and what type of car.
I remember we did that with chalkboard.
Could there be like enough positive charge to like rip your hair out?
Yes, that's called lightning. And if you have ever seen a tree that's been struck by lightning so that it explodes, what's interesting about it is it's not that sharp. You mainly have little wood chips of uncharred wood. And the way that happens is the lightning literally contributes a lot of positive or negative charge to that tree, and the tree literally rips itself out as the wood tries to get away from each other. Wow. The wood is just trying to get away from each other.
That's how
Electric force. How electric what?
that's how you could weaponize electricity.
Well, yeah, it just, yeah, it's kind of random. It's like being hit by lightning or something. Yeah.
Are there any like slow motion videos of a tree getting struck by lightning?
Uh-huh.
Are there any slow motion?
Probably.
How come like a human hasn't exploded?
Good question. Humans conduct better than wood do. Humans are better conductors, especially if they're wet humans. And so when lightning strikes a human, rather than being stored up in the wood and then out, what happens is most of that current goes straight through the human, down through the foot to the ground.
What if they were not like, they weren't grounded?
If they're not grounded, they're unlikely to be struck. If they are struck, it could be pretty serious.
So wait, when you get struck by lightning, it's not bad.
Well, so I don't know how many lightning strikes there are per year and how many fatalities. It's bad, but it's not always fatal.
So it's just like if you're not grounded, then it's worse.
If you're not grounded, as I said before, if you're not grounded, you're unlikely to be struck. Because lightning is going to take the path of least resistance. So if you're not grounded, what's going to happen is that the path of least resistance would have to be through you and down to the ground, and there's probably a better path somewhere.
So basically, if it's raining and you just start jumping up and down, you're less likely to get hit.
Yes. I mean, you would decrease your grounding time by about 10% like that. But you can't just boing, 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 right? You gotta gather yourself and then jump and eventually get tired. And
And then you're sitting down.
or, yeah, sitting human.
So if you're in the middle of the field, the building better do.
Lying down is a better thing. Lowering yourself, making yourself further away from the cloud. Okay, so where are we? We're comparing the gravitational potential energy to the electrical potential energy. Now here's what I want to observe. The part that I have circled here, mg for the gravity and QE for the electrical field, is the contribution of the actual physical waterfall itself, is the contribution of the plate of positive charge to my potential energy. You see what I'm saying? It takes two objects to have potential energy between them. You don't just have an object with potential energy. You have to have two objects that are in a relationship to one. And the contribution of the bucket of water is its mass. The contribution of my charge is its charge. But the contribution of the positive plate here is Q times, is equal to field times distance, E times T. And the contribution of my waterfall is equal to G times H. I said it was the circle part. I was mistaken. What I meant was this part here is the contribution of the waterfall, is the contribution of the positive plate. Okay.
So not the charge.
Not the charge, right. That's the charge's contribution, obviously. And so we would call, in this case, the G times H, the gravitational potential of the waterfall. It's not potential energy, it's like potential energy, but waiting for a mass to actually be there, to actually have potential energy. You see what I'm saying? It's a dry waterfall. It's got potential, but it's not going to have any energy until you actually put a mass there. In the same way, this point right here, point A, is going to, or point B, either one, is going to be at a point of electrical potential, but it won't have any energy stored in it until I actually put a charge there. So we're going to call the E times D the electrical potential, and we're going to use the symbol V, which is short for voltage, as our symbol for electrical potential. Electric potential then is energy divided by charge. And 1 joule per coulomb is going to be the same as 1 volt. So if I have a 9-volt battery, what that means is that that battery has enough oomph, you'll pardon the lack of technical term, so that if I place a coulomb of charge at the positive pole, it will have 9 joules of potential energy relative to the negative pole. By the way, on a 9-volt battery, you all know what I'm talking about.
That's wrong.
Which one is the positive, which one's the negative?
Positive, the big one, right?
Positive one is the little one, and the big one is the negative one. Yeah. The big one's the negative one. And how do I release that energy? I release that energy by connecting one to the other with a piece of metal in some way, by allowing charges to flow from the plus to the minus.
If you were going to a transformer, could you make it be like having more of a shop?
If you hook a 9-volt battery up to a transformer,
No, I mean, like, ones like if you get the rechargeable batteries, you take it out, like that, you can read it wiring. Could you expect to have cases of charge?
Okay, so we want to distinguish between two things that I've been talking about here, and one is charge, and the other is electric potential. And the electric potential is measured in volts. And a 9-volt battery has 9 volts of potential because of the particular substances that make it up. Okay. In the case of robot batteries or car batteries, those are lead and lead oxide, lead fluoride. And it gives you 12 volts. Charge is the amount of charge that is stored in that battery. So how many of you have ever wondered why a 9-volt battery is this little tiny thing, and the 6-volt lantern batteries are these big, huge, humongous things? You know what I'm talking about? Yeah, and that's always seemed really weird. Why is a really big battery a 6-volt, a little tiny battery a 9-volt? And the answer is that the size does not determine the voltage, it determines the total amount of charge that's stored in it.
It's basically the last one.
So it lasts longer. That's exactly right. So we use a big old 6-volt battery to drive things like lanterns.
Could there be a small 6-volt?
Sure, absolutely.
Are there?
Yeah, yeah, there are. And an easy way to do it is to take a bunch of double A's, which are 1.5 volts, and just stack them up. And then you get 1.5 plus 1.5 plus 1.5 plus 1.5, and that's 6. So when you put in 4 AAA batteries into the back of your calculator, you're creating, in essence, one 6-volt battery.
They're double A's.
I think the AAA's in the back of the calculator.
Why are there?
Really?
They're
They're
on. They're just rare.
Wait, what?
Oh, you're right, there are triple A's.
Yes.
Wait, what kind of battery?
What's that?
He's saying they're not like stacked.
Oh, I see. Yeah, so
They're like in a brick.
Except that it's like positive and negative.
good. So let's talk about that for just a minute. One way that we are going to diagram this to get a sense of it is we're going to draw a battery or anything else to be like a waterfall. We're going to use a waterfall as an analogy for our batteries.
Oh, it seems very different.
Uh-huh.
Can you answer the question, if you hook the 9-volt up to that transformer, like, would you shock someone, like, going into it?
No, that's what I was going to say, is that if you hook up a 9-volt to a transformer that whose output is 12 volts or something like that, you'll blow up the battery.
How many volts does an electric car use?
Good question. I don't know what the voltage of an electric car battery is. My gut is to say 12 volts to be consistent with other car batteries, but I'm probably wrong on that.
Look it up.
Yeah, thanks. So our waterfall analogy is going to emphasize the relationship between gravity and the mathematical analogy between gravity and voltage that I was talking about earlier. We're going to think of on a battery or anything else as the positive voltage is higher than the ground or the negative side there. So we're going to call the point that has 0 volts the ground, and sometimes you'll see a symbol in a circuit that looks like this. Looks like that.
It looks like a,
Looks like a little upside down Christmas tree or something.
so it's like,
It's kind of like the Wi-Fi symbol with the line on something.
Yeah. Kind of like that. Except the Wi-Fi symbol is supposed to be curved lines going outwards. This is supposed to be straight lines. Yep. And so ground is simply, as we did with gravity, is simply the arbitrarily chosen 0 point for our energy. And then any battery that has its minus side hooked up to ground is going to have its plus side higher than the ground. And so we picture charges falling off the cliff, and when they fall off the cliff, then they release their energy. Does that make sense? Can you picture it with gravity? You've got a cliff.
yeah, potential energy.
Yeah, exactly. So imagine by analogy, you have charges, and those charges are being pushed by something, a positive voltage. And so,
They have like acceleration time and stuff.
yeah, exactly, all of that. And so when they are able to fall off the cliff, so to speak, then they get a certain amount of energy, and they go through. And we call that electric current, the flow of charge. So the drop in voltage right here causes a flow of charge. Physically, here's what this looks like. I have my AA battery, right? There's the plus side and there's the minus side, right? And so I have charge stored up, and it's actually stored in chemical bonds. And now when I hook up, say with bare wire or through some circuit or something like that, it gets hot, yeah. AA's, they have enough internal resistance so that they don't blow up.
For AA batteries, why is the big, like the bump side plus and minus on both sides?
It's just convention.
Just
Yeah. I don't know the history of it.
Okay, this is just like on topic, because we were talking about electric cars. Have you heard of Tesla?
Yeah?
They have an autopilot.
Nice.
Is that the in charge of the 240 volt charger?
Yeah, that doesn't really tell you though, because what happens is that 240 gets transformed down to whatever voltage
Okay.
the
Seems
combat
like a lot.
needs. Yeah. Okay. And so one way that I could see current flowing, perhaps, is to put an LED in between here. Now, an LED looks like this. You've seen them all, like that. Here's my actual circuit. The LED would need a little bit of protection, so I might actually put a resistor in here, but I'm going to pretend it doesn't for just a moment. And so if I hook up the LED in the correct way, then we will see current flow because the LED will actually turn on. And the reason that it is turning on is that electrons are going through that LED, and as they go through the LED, some of them are bumping up to a higher energy level and then falling back down. And when they do, they release photons of light, as you talked about in chemistry last year. Are we good so far, Alexis? Does this make sense? Okay. Now the way that we would diagram this is in a picture called a schematic, and you guys are going to get very good at doing schematics. We're going to represent the battery as a series of plus and minus plates or layers like that. And the long side is going to be the plus side, and the short side is going to be the minus side. And often we will put the value of that battery in our schematic. And then we're going to show the wire, like so. And then each component is going to have a particular symbol. In the case of the LED, the symbol happens to be this right here.
There's like certain symbols for different.
For different types of components, that's exactly right.
Do we have to name
There are only a few of them, and you'll see them a lot.
I'm assuming LED is one of them.
And LED is this guy right here. This is actually any kind of diode, and to be a specifically light-emitting diode, you show a little arrow with light coming off of it, like that. So there's an LED for you. And this guy is a battery. So that's our schematic. Now I'm jumping ahead a little bit because I'm not focusing too much on schematics right now, but I did want to explain, Alexis, what's going on here. Once I have my plus connected to my minus, now current is going to flow because it is the drop in voltage that causes charge to flow, just like that. Does that make sense?
It's just going down. Instead
Yeah, right. Well, we're diagramming it as down because this is energy that we're looking at as our axis here. Physically, what it's doing is going through the wire like that. And as I mentioned before, you remember that the convention charge goes plus to minus was invented by whom? Who was it that decided charge was going to go plus or minus? It was Ben Franklin, that's exactly right. What happens in reality is that actually it's the electrons that move, and the electrons go from minus to plus. So the real picture is that you actually have electrons going against the arrows from the minus side to the plus side. But the math works out just fine if we say that charge goes from plus to minus and read it like that. So we're gonna say that current goes from plus to minus. We understand that what current really is the backwards flow of electrons. Yes. How does it work out with a car battery? Well, this might surprise you, but a car battery is actually not that high in voltage. It's only 12 volts. So I can take a car battery and touch plus and minus with my hands and no problem. But the car battery is also designed so that if you connect plus to minus with a wire, then you can get a lot of current out of it really, really quickly. And the result is that if you short a car battery, you will get a huge spark at best, and you might get a small explosion at worst. So you don't want to connect plus to minus on a car battery, but you can handle it with your hands, and there's no problem. And that illustrates the difference between voltage and current. Lots of current, low voltage for the car battery. Does that make sense? Contrast that with like the phone line or the wall outlet. The wall outlet produces about 117 volts. So if you touch it with your hands, you're going to get a pretty sharp shock out of that. The phone line is interesting because plus to minus on the phone line is 40 volts, which is just right about at the level of human perceptibility. So if you touch across the phone line plus to minus, which is hard to do because it's a little jacking solution, then you're going to get a kind of a healthy sort of vibration. It feels very strange. And that's because it has a higher voltage than your car. Okay. The only thing left for us to do is to consider the electric potential that is created by a single charge. Here, I've been talking about lots and lots and lots of charges all working together in a battery to produce electric potential. What if I isolate just one single charge like a proton or an electron? The electrical potential of a single charge. Okay, so here I've got my single charge, and as you know, we have electric field lines that are going to come out of it. And our big equation is that the change in potential energy between two charges is equal to the charge of one times the change in electric potential created by the other. So that if I put a positive charge right here, these two positive charges are going to repel each other. And if I now move that positive charge from A to B, like that, then I'm going to have to do some work to make that happen. Well, how much work? Well, it gets complicated because the force that is involved is K times Q0 over R squared, right? Everybody agree so far? And we even graphed that and said that the graph of our force looks like this. In other words, the force is really weak out at large distances and it's strong close in. Now here's my problem. As I move from point A to point B, the value of my force changes. I have a changing force. And you guys remember what we had to do when you have a non-constant force. How do you compute the total work?
You take the crap.
No, you don't take crap.
Take a point.
What do you do? How do you find
Right?
work when your force is changing?
Force times distance.
Yeah, but what force? Do I take the force here, or here, or here, or here. See, the value of my force is changing, so I can't just say force.
The
The average,
I could do average if I knew the average, right? But the average is not going to be endpoints added and divided by 2. How do I find total?
Slope.
Go. In terms of potential energy, yeah, if I do it.
You do the area.
You need an area. That's what you need. Calculus student.
That's how.
So the work is equal to the area. Now, computing that work requires some super secret calc foo. Your calculus students know exactly how it's going to be done, right? And so you can see here, given that these three are constants, you can see what we're going to what we're going to end up doing. And it's not too terribly hard because that's r to what power? It's r to what power?
2.
No. What power of r is that?
Oh, -2.
Negative 2, of course.
oh, because it's
It's in the denominator. Right, that's exactly right. So for you calculus students, we would say that the work is equal to the right.
technically derived.
Gosh.
Why don't you know these
What is
things?
you define the slope of the
All right, so if you are not in calculus, just hide your eyes, children, hide your eyes from this. But if you are calculus students, we would integrate from A to B. Notice even though A is larger, we're going to integrate from A to B, KQQ over R
When you
squared.
say I negative b there.
Yes, exactly. Now, for you non-calculus students, we're just going to work our calculus magic here. Here we go. And so what we end up with is this expression right here. Now this is a pretty awkward expression. So what we're going to do is we're going to define it in terms of an electric potential function. It's going to be just like our gravitational potential function, but it will have a different mathematical form. When we did gravitational potential energy, we had an expression for the potential. What was it? U equals yeah, for gravity. MGH, exactly. We're going to do the same kind of thing with our charges here. And the way that we're going to do this is we're going to set our 1 point, our radius out here, out at infinity, so that we can compute the amount of work that it would take to get all the way from infinity all the way to point B right here. And we're going to call that the amount of potential from infinity. We're going to say the potential out of infinity is 0. We're just going to set our 0 point there. So that when we do, the potential energy, U, is going to be equal to KQQ over R. And therefore, the electric potential, which is potential energy divided by the test charge, is going to be KQ over R. This is the electric potential for a single point charge, a single charge. Now, what does this mean? Here's what this means. Conceptually, this means that I'm going to visualize a positive charge as being like a very steep hill. So visually, I'm going to picture a positive charge as being like a very steep hill, like this. And if I place another positive charge next to it on that steep hill, what is that positive charge going to do? It's going to fall away. You see it? And because the hill is very steep, it's going to fall away very quickly. And the shape of this hill is the shape of the graph of KQ over R on either side. Now the weird part about it is mass only comes in one flavor, positive mass, right? But charge comes in two flavors, positive and negative. So if I place a negative charge on the hill, what strange thing happens?
It goes up.
It goes up. So the difference between electricity and mass is basically found right here. That for electricity, you can have charges that go uphill. We call them negative charges. But you can see why. You can see how that works out.
Teachers,
And that's
pardon the
enough.
interruption, the boys